Today's speaker is Michelle Chu from Texas. She's going to talk about special subgroups of Bianchi groups.
Okay, so thank you so much for having me. First, I'm just going to set down some notation. So throughout this talk, M is going to be a hyperbolic 3-manifold or orbifold. So we can think of it as a quotient of hyperbolic 3 space by its fundamental group. And sometimes I'm going to use gamma to denote its fundamental group. Okay. So the main purpose or the main theorem that I'm going to talk about is really a way to quantify special groups for these 3-manifold groups, and in particular for the Bianchi groups. But before I do that, I'm going to give you a little bit of an introduction as to why we should care about these types of groups. So let me just go ahead and start telling you why we should care about these. So the first thing is, this is the virtual Haken conjecture. So this was a question of Waldhausen in 1968. And so this question is, let me write this down here. So does every aspherical 3-manifold virtually contain an embedded surface? So virtually here means that there is a finite sheeted cover that contains an embedded surface. And so, this question has been around for a while, but until pretty recently, it was very well known for everything except hyperbolic 3-manifolds. So we're going to consider hyperbolic 3-manifolds. But there's another question that's related. Virtual fibering.
Is this an essential surface? An embedded essential surface?
Yes. Let me say it here. Essential. If I forget to say essential later, you should assume that I'm always talking about essential surfaces. Okay, so the other one is a virtual fibering conjecture. And this one is a little bit bolder than this one. So this was a conjecture of Thurston in 1982. And he asked if, and this was specifically for hyperbolic 3-manifolds, does every hyperbolic 3-manifold virtually fibers over the circle? Right. So then this question, well, this is called virtual Haken because a Haken manifold is one that contains an embedded essential surface. And so to virtually fiber over the circle, this is the same thing as saying that M is a mapping torus. Which means that you can think of it as you have some surface, you cross it times some interval, and then you glue top to bottom via some homeomorphism of your surface. Okay? So this is definitely stronger than this because here you not only have an embedded essential surface, but you have your manifold looks like this. Okay. So this one should be stronger. Yeah. So these were conjectures, but now they've been proven. But before I tell you a little bit about that, Let me just first tell you about some group properties. So let's say here, some properties of groups. Okay, so the first one, let's say here G is a group. So the first one that I'm going to tell you about is that if you have H, a subgroup of your group, then H is separable if for every element in your group that's not in this subgroup, you can separate your subgroup and this group. So what that means is there is some finite index subgroup of G such that it contains it contains H, but it does not contain G. Okay? So the picture that you should be thinking of is like if this is your group G and you have this element G that is separate from like this group H, the subgroup H, then there is a large subgroup of G, let's say all of this, that contains H, but doesn't contain this little g. Okay, so that's what it means for a subgroup to be separable. So then we say that G, the group itself, is subgroup separable if all of its finitely generated subgroups are separable. Okay, and this property is also called LERF. So LERF here stands for locally extended residually finite. And residually finite means that the subgroup that has just the identity is separable. And locally extended means that we're extending that property to finitely generated subgroups. Okay? So that's LERF. And maybe you've heard before other types of properties that are similar to this one. For example, there's QSurf, which means that quasi-convex subgroups are separable. There's also GFurf, which means that geometrically finite subgroups are separable. But anyways, today we're going to be talking about LERF in particular. Okay, and then there's one more property that I want to tell you about, but I'm not going to give you the group definition for it, but I'm going to give you the definition for this property when you already have that your group is a fundamental group of a three-manifold. So we say that G, which is the fundamental group of this three-manifold, is Reefers. Okay, so this is the same RF for residually finite, but this is residually finite, rationally solvable. So G is Reefers. Let's say if there exists a cofinite tower. So we have something that looks like this. So these are subgroups. So these correspond to covers. Of your three-manifold, I ran out of space down here, such that, such that mi plus 1 is a finite sheeted cover of mi. So let me say a little bit more. Oh, actually, let me take out this word sheeted and just say this is a finite cyclic cover. Dual to some non-separating surface. And cofinal here means that if you intersect all of these, you just get the identity. And let me draw you a picture so you have a better idea of what I mean by this. So if you have a non-separating surface in your manifold, then there's also a loop that goes around it exactly once. So you kind of have a picture like this. So let's say here is some surface, and you have some sort of loop like this. And what you're doing in the cover is that you are unwrapping this loop in this way. So let's say you could have something like this. Okay? And you should notice that if we were to pick the same surface again and keep doing that, it wouldn't be a cofinal tower, because at the limit you'd have some sort of infinite cyclic cover, and so that wouldn't give you a cofinal tower. So you're picking different surfaces each time. Okay, so this is what it means to be Reefers. Okay, so any questions so far? Okay, so I'm going to tell you why these properties of groups are useful for handling these two questions. Okay, so the first reason, this is a theorem of Peter Scott in 1978. So what he says that if your fundamental group is LERF, then immersions lift to embeddings in finite sheeted covers. Okay, so let me tell you a little bit about how this works. So imagine you have some 3-manifold, and you have some immersed surface in there. So don't really know how to draw it, but let's say it's some surface that runs into itself. When it runs this intersection with itself in here, what it corresponds to some element that's in your fundamental group, but that doesn't come from the surface group. So then you should see that LERF should be really useful, because we can find, using LERF, we can find a finite index subgroup of your fundamental group where the element that came from that intersection is no longer there. So in that finite cover corresponding to that group, you're going to get rid of this intersection. So this is really where this comes from. Okay, so that's really the idea of what is going on there. Okay. Oh, and one more thing I want to say about this, that is in this paper, he also showed that surface groups are LERF. LERF. Okay? And the way that he showed this was by embedding them into a right angle Coxeter group. Okay. I'll remind you what that means in a little bit. Okay. So you should see that if we have our 3-manifold, and we know that there's an immersed surface, and we know that it's LERF, then we get virtually Haken. Okay. So now let me give you another theorem to show you why Reefers is useful. So this is a theorem of Jan in 2008. So this is a bit more recent. So what he said is that if your fundamental group is Reefers, that means that it is virtually fibered. Okay? So the way this sort of works is that, so you're doing this type of picture, and if you happen to have, so if this was not already fibered, that means that you have some pieces in here that are not so nice. And when you keep doing this, you're trying to get rid of those not nice parts. So eventually you should get something that is nice. So in fact, he shows that in this tower, at some point, one of these is going to be fibered. So that's actually what he shows. So Reefers would be useful for that. So then again, if we have Reefers, we get virtually fibered. So that would be a nice property. But you should notice also that in the definition of Reefers, you already need to have a surface in there. So Reefers is stronger. Virtually fibered is stronger than virtually Haken. Okay. Okay. But then, okay, so now I'm finally going to tell you how both of these conjectures were resolved. And this is a bit more recently. So in 2012, what Agel proved is that closed hyperbolic three-manifold groups are virtually special. Okay, so this is the special that you can see in the title. Okay, and what this means, so let me just tell you here, is that they embed nicely in a right-angled Artin group or right-angled Coxeter group. Oh, virtually. Well, that's what it means to be special. Okay, so let's say that here. So let me just quickly remind you what a right-angled Coxeter group is. So what you should think of when you think of right-angled Coxeter groups is you should think of a reflection group where you have some number of reflections. If you have a reflection group and you have two reflections you have these two planes that meet at a right angle, then that means that when you do, let's say, xi, xj, that this will give you the identity. So let's say something like this for some of the pairs. Anyway, so this is what an abstract right-angled Coxeter group looks like, but you should think of it as reflection groups in some sort of polytope with right angles. It doesn't have to be three-dimensional. It could be any dimension. Okay, so this is what you should think of when you think of that. So he showed this, but the important thing is that this implies Lerf, and it implies virtually Reefers. And it ends up also giving the virtual Haken conjecture and the virtual fibering conjecture. But there's a lot of work that goes into showing all of this. So I think it would be unfair to just say that this is Agel. So let me just write down some names here. So a lot of it was done by Danny Weiss, but not just him, but also him and his collaborators. So Haken, Weiss, This is actually where they define what special means. Let's say Eagle, Groves, Manning. Markovich. And lots of other work goes into this. But Markovich, what they showed is that these closed hyperbolic 3 manifolds actually contain lots of immersed surfaces. So if you have at least one on your LERF, then you get virtually Haken. However, you needed lots of them to say some other stuff along the way that gives you here. So it is important that there's lots of them. And I also want to say that recently there's been some work by Cooper and Footer where they do this type of result for cusp hyperbolic 3 manifolds. Okay. Okay, so what you should take away from all of this is that it is really nice to embed in a right-angle arcing group and in a right-angle Coxeter group. But we know that this is a virtual property. So let me just write down now what the motivating question is for now. Motivating question is how far, so how far do you go to get these nice properties? So special, Haken, fibered. Okay. So in particular, if you're given something, what index you need to go to get these nice properties? Because we know we virtually have these properties, but we want to know that. Okay. So this is a question that I want to answer today for special. For a particular class of groups that are called the Bianchi groups. Okay, so the Bianchi groups are the groups gamma D that are PSO2 OD. So let me tell you what this is. So this is going to be the ring of integers. In these quadratic imaginary fields. So if we want to look at distinct ones, then we really should think of D as positive square-free integers, okay? So, and this ring of integers, sometimes it looks like what you want it to be, but sometimes you need to add something more. So this is whenever D is equivalent to 1 or 2 mod 4, and this is when D is equivalent to 3 mod 4. So it's never equivalent to 0 mod 4. Why is that? Square free. Okay. Yeah, okay, so these are the Bianchi groups, so you can see that these are subgroups of PSL2C, which we can identify by the orientation preserving isometry group of the hyperbolic 3 space. So if I take their quotients, this is what we're going to call the Bianchi orbifolds. So these are orbifolds because these groups have torsion. Okay. So why should we care about Bianchi groups? Well, first of all, they're pretty nice. They've been studied for a long time, but there's a lot of nice structure to them, and the nice structure is something that we call being arithmetic. And in fact, if you take any arithmetic hyperbolic 3-manifold, it has to be commensurable to one of these Bianchi orbifolds. So they're pretty important, but they're important for other reasons too. So let me give you an example. So if you look at the fundamental group of the figure 8 knot, I have to make sure I draw this correctly. Yeah, this is fine. Okay. So the complement of the figure 8 knot. Yeah, this is the figure 8 knot. If you look at this complement, this is contained in gamma 3, for example. So here's another interesting example. If you look at the complement of the Whitehead link, which I think is this. No. Maybe this. Okay. Then this is contained in gamma 1. Okay. So these are some of the reasons why you should care about Bianchi groups. Okay. Okay, so here's a theorem. This is Agel, Long, Reed from 2001, but I'm actually going to combine a couple of theorems here together. So let's also say Long, Reed 2008. So what they showed is that Bianchi groups are Lerf. And they virtually retract to their geometrically finite subgroups. Okay? So the way they actually stated this in 2001 wasn't exactly like this. And then virtual retracts were introduced in this paper, but independently also by Haken in the same year. Yeah, but so the key to showing this was to show that they virtually embed in a right-angled Coxeter group. Okay, so this was the key step for proving all of this, okay? So actually this says that they're virtually special, but you should notice here that this 2001, this predates a lot of the virtual specialness conditions. Actually, virtually special was defined by Haglund and Weiss, I think sometime after this. Okay, so they wouldn't have used that wording, but this is what they showed. Okay, however, in their proof, you know you virtually embed in here, but it doesn't really tell you how that virtual embedding goes. So that's what I'm going to do. So let me move on to this side. So now I'm going to say this theorem. So the Bianchi group gamma D has a finite index subgroup, which I'm going to call delta D, such that first is the index. So the index sometimes is 48, sometimes it's 288, and sometimes it's 480. So this is when D is 1 or 2, mod 4. When D is 7, mod 4. When D is 3, mod 4. Okay, so immediately you should notice that there's a bit of a difference here, and this really comes from this.
More 8?
What?
Do you mean more 8?
Yes. 8. Thank you. Okay. Oh, there was a few other things that I wanted to say. This is true. This group retracts to the free group on 2 generators, and this group is Reefers. Okay. So being virtually special only tells you that you're virtually Reefers, but in this case, this group is Reefers. Okay.
These numbers sharp?
No, it's definitely not sharp. So actually I can do slightly better than this. Like you can maybe divide this by a third. However, the nice thing about this is that gamma D is a congruence group. So it's not a principal congruence. Oh, well, I'll tell you in a bit. And I'll tell you how it could be slightly improved, but I still wouldn't know if that's sharp or not. Okay. So you should notice that the D doesn't, I'm sorry, the index doesn't depend on the D. So I think that's kind of nice. Okay. Okay, but before I do that, I should define for you what a congruence group is. So let me do it in, so I'm going to define it not in general, but whenever you have a group that is contained, in GLN-C. So you're assuming here that the entries are integral. Then you look at this is called the principal congruence subgroup of level n. So these are going to be all the elements in your group such that it's equivalent to the identity mod n. Okay, so this is entry-wise. And you can say that's more general for when you have a ring of integers here and look at ideals instead of just these numbers. But this is what this is. So let me give you a quick example.
Different ends.
Yeah, let's say M. Sorry. Okay, so let me give you a quick example. So if you take the modular group, SL2C, and you look at its principal congruent subgroup of level 2, then this group is generated by these matrices. So you can see that this is equivalent to the identity modulo 2. There's also this one. And there's this one. Okay? So this is what this group is. But you can also look at, say, PSL2C. And this congruent subgroup is generated by these two matrices. Yeah. But really, they're equivalence classes because we're doing PSL2 here. But this group is the free group cross C mod 2C. And this group here is the free group. So maybe you should see this as a little hint to this part. Okay. So that was this. Okay. So in the remaining time, I'm just going to tell you a little bit of the ideas that go into this. And I'm going to say that a lot of the ideas come from the work here. So you should always keep that in mind. Okay. So here's the first thing that I'm going to say. If you look at, I'm going to define Fi to be a quadratic form. So this is the notation that I'm going to use for a diagonal quadratic form. So that means, the corresponding symmetric matrix looks like this. Okay? And let's say there's I of these. So this is where this comes from. Okay? So this is a quadratic form of signature I1. So that means that if I look at the special orthogonal group, and I look at the identity component that preserves this form, this gives me the isometry group of HI. Okay? So that's the first thing that you should know. And if I take this and I look at the integer points, this is a lattice. So the quotient is going to give me a hyperbolic orbifold of dimension I. Okay? So now here is the first thing. So this is the theorem of Everett, Ratcliffe, and Shams. So what they show is that if you take I in here, between 2 and 7, this group the principal congruent subgroup of level 2. This is the reflection group for an all right, oh, not much space here, hyperbolic Coxeter polytope of dimension I. Okay? So this group itself is a reflection group. So this group itself is a right angle Coxeter group. Okay, and this is something that Egel, Long, and Reed did notice. Well, they noticed that this group was commensurable to one of them, but they were able to say this explicitly. Okay, and actually this is a really nice family because if you look at, say, the dimension 7 one, all the faces are going to be the dimension 6 one, and so forth. So it's really nice. It's really nice. But also, I want to say that actually these hyperbolic Coxeter polytopes were well known, but they were able to figure out that this is exactly the reflection group. Okay. So that is the first nice thing. So the next thing is that the groups, gamma D, they are commensurable with a group of this type. But here, now the quadratic form looks like this. So this one is not diagonal. Okay? So they're commensurable in here, but we still have to think about how this commensurability works. But we have this, and this is really nice. And this is some work of, okay, I need to make sure I write these names down correctly. Oh, can't find it in my notes right now. But let me see if I can write these down correctly. There's Ostrad, Grunewald, and okay. So what they show is that if you take this group, this group is in fact isomorphic to not the Bianchi groups themselves, but a very closely related group. So in some cases, this is the Bianchi group itself, but not always, okay? So that's also, so this is pretty nice. We have this nice isomorphism. And they also give you a way in which you can construct the explicit isomorphism. Okay, so the next thing I'm going to tell you, you should see as sort of what brings this all together. So here's what I'm going to say. If I take the quadratic form of, if I extend the quadratic form, QD, by this diagonal quadratic form, okay, so now this used to be one that had signature 3-1. This one has signature 6-1. This form is equivalent to F6, okay? So what that means is that there exists some matrix A such that if you conjugate, if you take the conjugate of this group, you get the other one. Oh, sorry, this is P. Okay, so this is how we can relate them. So this is, you don't get the integer points exactly, but this is something that you can, well, one could figure out.
What kind of matrix is A? Does it have coefficients in?
Oh yeah, let me say that. So they're equivalent over the rationals. So it's in here. Okay, these forms are equivalent over the rationals. Okay. Yeah, so this is really nice because now from here, if we can understand this picture really well, then we can get something of the sort that we have over there. So let me just end a little bit by telling you a bit more about this, this retraction here. So yeah, so let's say ... and you get the theorem. Okay, great. Okay, so let me just say a bit more about the retraction. So one thing that is true, I think I didn't mention before, is that when you have a group that's virtually special, then that also means that you have, that your group virtually retracts to its geometrically finite subgroups. So the free group is a geometrically finite subgroup. So you know that there is some subgroup that's going to retract to there. But this group, this is the group itself that retracts. This group itself retracts to there. So here's the, I guess it's kind of like a nice idea. But if you have some sort of right-angled polytope, let's say P, and you have, let me not say gamma, let's say G is its reflection group. Then what's also true is that the faces are right-angled polytopes. So these are one dimension down. And you can continue to do this. So because we are right-angled, we have this very nice, right-angled. The point is that if you have a reflection on this face, then how does that act on this other face that it meets? So it's still fixing that face, but it is reflecting a side of this face to the other side, right? So you should realize that a reflection on a face is a reflection on, say, like the edge of a face that's adjacent to it. So that's really where this idea comes from, because you can take your right-angled polytope and retract it to, you can retract your reflection group to the reflection group of the faces, and then you can continue to do that until you get down to whatever it is you want. So that's really where the idea comes from. And this turns out to be true because this group comes from PSO2C, 2, and this is equal to the intersection of the subgroup PSO2C intersected with delta D. Okay, and one more thing that I want to say, and then I'll finish with that, is the reason I said earlier that you could do maybe slightly better. So the reason you can do maybe slightly better is because, in fact, you can include one extra element you can have the group that's generated by this and one extra element, and it'll still be special. And that extra element turns out to be this element. Okay, I'm going to end here.
Any questions?
Can you actually say what the group delta D is?
Oh, yeah, I think I did mean to say that, but then didn't, sorry. So let's say here that it turns out that if you take PSO2 I'm going to take this group, and I look at the principal congruent subgroup of this group. So this is, in the cases when D is equivalent to 3 mod 4, this is not going to be a principal congruent subgroup of the Bianchi group. However, it's still a congruent subgroup because it's contained in here. Okay, this is what the group is.
Do you know, so when you get this tower of covers where you, and then eventually you fiber, do you know anything about like the index where you fiber or bound?
No, I don't know anything. Yeah, I don't know anything. The only thing that I know is that you can look at some refinement of the tower that you get from 2, and the prime set split over 2. That is going to be a Reefers tower. But this is something that was in Eagle's proof that Reefers is a criterion for visual fibering. He said that you take this right-angle Coxeter group, and then you look at this nice subgroup that's Reefers, and a tower that's going to work for you is one that's over 2, basically. Yeah, but no, I have no idea. I wouldn't know how to do that, but I would like to.
Any other questions? Well, let's thank Michelle again.